Jai Hind students, welcome to my YouTube channel. Students, there is nothing more true in your life than taking your own decision, for it in turn will decide the course of your destiny. It will decide the course of your future. The decision which you have taken will decide whether in future you will be happy or you will regret it. Whether this decision taken by you will lead you closer towards your goal or lead you farther away from it. There is a simple way out too. That is, you can follow in everyone's or everybody's footsteps, or students, you can do what 1 in a million does. So students, all the best for your future, and I hope you will trust your abilities and will do wonders in your future, right? So with that, let's start today's session. Today we'll be discussing a very important topic, which is Ampere's Circuital Law. We are over with Biot-Savart law and Laplace law. Now we will discuss Ampere's Circuital Law. There are various applications of this law, but today in this session we'll be discussing the statement as well as the mathematical verification of this law for both symmetrical as well as asymmetrical loop. Right, students? So let's first concentrate on the statement of Ampere's Circuital Law. Now look, like Gauss theorem, it was applicable for any closed surface. Ampere's Circuital Law, it is applicable for any closed loop. That closed loop may be perfectly circular or it may be of any irregular shape. Right? So let's concentrate on its statement first. Okay, this is a horizontal plane. Let us consider this to be a horizontal plane. And this is a current carrying conductor. This is a current carrying conductor. Suppose current I is flowing through this straight conductor. Right? This is current I flowing through this straight conductor. Right? Okay. Now Ampere's Circuit Law states that the closed line integral of magnetic field is numerically equal to mu naught times, it is the absolute permeability of free space. So it is numerically equal to mu naught times the net current threading through the loop. Net current threading, passing through the loop. This is the statement. So we'll discuss each and every meaning of this statement, right? So Ampere's Circuit Law states that the closed line integral of the magnetic field is numerically equal to mu naught times the net current threading through the loop. Mu naught is, we are aware, it is the absolute permeability of free space. Now this is a current carrying conductor. Let's consider a loop over here. This is a loop. This is a loop, right? So in this case, the closed line integral of the magnetic field, that is B vector dot dl vector. This symbolizes the closed line integral, right? It is read as the closed line integral of the magnetic field. This is the scalar product. It is equal to mu naught times the net current, mu naught times net current threading through the loop. This is the statement. Now here, through this loop, the net current threading through the loop is I. So for this particular case, the mathematical statement of Ampere's Circuit Law would be B vector dot dl vector is equal to mu naught I. So this is the mathematical representation of Ampere's Circuit Law. I repeat, students, Ampere's circuit law is applicable for any closed loop through which some net current is threading. So in such a case, Ampere's circuit law states that the closed line integral of the magnetic field is always numerically equal to mu naught times the net current threading through the loop, right? Here mu naught is, obviously we all are aware of it, mu naught is absolute permeability. It is absolute permeability of free space or vacuum. Absolute permeability of free space or vacuum. So this is considered to be vacuum, and its value we are aware, it's constant. It is 4 pi into 10 raised to minus 7 units. We have already discussed. It is Tesla meter per ampere. Tesla is the SI unit of magnetic field. So this is the statement, and here I would like to mention some very important aspect. dl, it is the small elementary portion of the loop under consideration. This is dl. Suppose this is a small elementary portion. This is dl, p to q. So dl is the small elementary portion of the imaginary loop under consideration, right? And students, remember, this elementary portion, wherever possible, is to be measured along the direction of the magnetic field. Now look, we are aware of magnetic effects of current. Whenever there is a current carrying conductor, so magnetic field will be established around its vicinity. So applying right hand thumb rule, if the thumb indicates the direction of the flow of current, then the direction in which the rest of the fingers curl, that gives the direction of the magnetic field, isn't it? It will be like this. So due to this current carrying conductor, the magnetic field at here, at this point, would be like this, tangential, right? So here dl, which is the elementary portion, vanishingly small, infinitesimally small elementary portion of the loop, that is to be measured along the direction of the magnetic field wherever possible, so that the angle between magnetic field and dl vector becomes 0. So dot product in such a case will get eliminated because cos 0 is 1. Clear, students? So dl is the length of the elementary portion of the closed loop under consideration, and this elementary length is to be measured along the direction of the magnetic field wherever possible. Clear? So now, since we have done this statement of Ampere Circuit Law, now let's try to mathematically verify this statement, both for symmetrical loop, like we'll consider the loop to be circular, and in the second case we'll prove the same statement in case of some closed irregular asymmetrical loop, right? So let's deal with case 1 then. So we are going to prove Ampere Circuit Law for a circular loop. So we'll consider a straight current carrying conductor, maybe infinitely long, like this. Case 1 for circular loop. We'll prove Ampere Circuit Law for circular loop, right? This is a straight current carrying conductor, maybe infinitely long straight current carrying conductor, carrying current I in the direction upward as shown in the figure, right? Suppose this is the loop under consideration. We are considering a circular loop. This may be considered to be a horizontal plane, like this. This is a horizontal plane. Just to give it a three-dimensional appearance, I have done it like this, right? This is a horizontal plane. And suppose we consider taking point O as center, and let's see, say point P as any arbitrary point, and OP is equal to R. We'll draw a circular loop. This is a circular loop under consideration. Clear, students? Now what to do is, we'll consider a small elementary portion over here. Suppose this is PQ. This is small elementary portion. It can be considered to be DL, right? Now what we are supposed to prove is to prove closed line integral of the magnetic field, this is read as closed line integral of the magnetic field is equal to mu naught times net current threading through the loop. In this case, through this circular loop, the net current passing or threading through the loop is I. So for this particular case, it will be mu naught multiplied by capital I. Clear, students? This is what we are supposed to prove. So let's consider left hand side, which is closed line integral of the magnetic field. Now, as I have told you, whenever we consider a current carrying conductor, then magnetic field will be established around its vicinity, the direction of which is given by right hand thumb rule, isn't it? Magnetic field lines, we are aware, it's in the form of continuous closed loops. Magnetic field lines do not have any starting point, nor do they have any end or terminating point, isn't it? So current is flowing along this direction, so the magnetic field lines will be like this, using this rule. So magnetic field lines will be in the anti-clockwise direction, like this. So at point P, the field line would be like this. This is the magnetic field, right? So as I was told, DL, it is also to be measured wherever possible along the direction of the magnetic field, right? It will obviously be perpendicular to the radius of the loop. So let's solve it. B dl, this is the scalar product. A dot B is AB, cosine of the angle between them. So magnitude of B, magnitude of dl, and cosine of the angle between these two. What's the angle between these two? It is 0 degree. So it will be integration of B dl. So this dot product gets eliminated. Now one more thing, students. This magnetic field B, at any point, the magnetic field B, at any point on the circumference of this loop being equidistant from the straight current carrying conductor would be constant. So the magnetic field at any point on the circumference of the loop is constant, being at the same distance from that straight current carrying conductor. So B being constant, it can be taken outside the integration. So what we get is B closed by an integral of dl. Clear, students? Now B is the magnetic field at point P, which is at a distance r from this infinitely long straight current carrying conductor. We are aware of this value. We have done it in Circuital law, isn't it? The strength of the magnetic field at any arbitrary point P, which is at a distance r from an infinitely long straight current carrying conductor, is mu naught I divided by 2 pi r. So B is mu naught I divided by 2 pi r. And what about this integration of dl? If you join the small elementary portions and add them all, it will give us the total circumference of the loop under consideration. So circumference of the circular loop of radius r would be 2 pi r. So what you get? Mu naught I, which is equal to RHS. So this is the mathematical verification of Ampere's Circuital law when we make use of circular loop, right? So what is the statement? Again, let me repeat. Ampere's Circuital law states that the closed line integral of the magnetic field is numerically equal to mu naught times the net current threading through that loop, right? So that's the statement which we have mathematically verified. Clear? So we are over with the statement, and also we have done the mathematical verification for the symmetrical, that is circular loop. So we will prove the same statement for any asymmetrical loop. So let's deal with case 2 now. We will prove Ampere's Circuital law in the case of an asymmetrical loop. It's a loop, but it will be asymmetrical. Okay, let's do it. So case 2 for an asymmetrical loop. This is our objective, to mathematically verify Ampere's Circuital law for any asymmetrical loop. right? So again, let's consider this to be a horizontal plane. Just to give it a three-dimensional appearance, I am drawing like this. This is a horizontal plane. Students, you need to visualize it. So this is a straight infinite long current carrying conductor, carrying current I in the direction as shown in the figure, right? And students, this is any loop. This is any loop. This is any loop. Obviously, it is an asymmetrical loop. It is an asymmetrical loop. In the previous case, we have considered the loop to be circular, symmetrical. This is the case where we are considering the loop to be asymmetrical. This is point 2. Obviously, at every point on its circumference, its distance from the straight current carrying conductor would be different. And hence, at different points on the loop, the strength of the magnetic field due to this current carrying conductor would also be different. It won't be constant, right? So students, what we'll do is, we'll divide it into several parts, small parts, like this is of length dl1, and let us consider this of radius r1, and subtending an angle maybe d theta 1, right? This is another loop, maybe of length dl2, of radius r2, subtending an angle d theta 2. Clear? So, I will draw its enlarged version. So it is somewhat like this. This is dl1, this is point 2. It's of radius r1 and it is subtending an angle of d theta 1 at point 2. Then there is another small portion, maybe dl2, and it is subtending an angle d theta 2. And suppose its radius is, let us consider it to be r2. Understood now? So we can divide the loop into small elementary portions of radii r1, r2, r3 and so on, and subtending angles of d theta 1, d theta 2, d theta 3 and so on. Clear, students? Okay. Now what to do is, due to this straight current carrying conductor, magnetic field will be present around its vicinity, and the direction of which will be again in the anti-clockwise. Using this rule, the thumb points towards the direction of the flow of current. So the direction in which the rest of the fingers curl, that will give us the direction of the magnetic field. So it will be in the anti-clockwise direction like this. And as I told you, students, dl, the elementary portion, is to be measured wherever possible along the direction of the magnetic field. So here the magnetic field would be like this. This is suppose B1, over here suppose it is B2. At any point it will be given by drawing a tangent, isn't it? So dl1 would also be measured along the same direction, wherever possible. Here this is dl2. It should be measured along the same direction as that of the direction of the magnetic field. And here, as I stated earlier, at different points, students, the strength of the magnetic field due to this current carrying conductor would be different, because the distance of the observation point from the straight current carrying conductor would be different, and accordingly magnetic field at different points will be different, right? So let's consider left hand side, that is closed line integral of magnetic field. Now what to do is, this is the integrations, it is the expanded version of summation. We'll split up into n parts. So we can write it like this. Let us consider b1 vector dot dl1 vector plus b2 vector dot dl2 vector plus b3 vector dot dl3 vector and so on. Maybe the nth part, that is bn vector dot dln vector. Look, students, dl1, dl2, dl3, dln, these are the small elementary portions, the combination of which will make the entire asymmetrical loop, right? And these are the magnetic fields at any arbitrary points on those small elementary portions, and they are different. Accordingly, they are represented by b1, b2, b3, because the strength of the magnetic field at a point does depend upon the distance of the observation point from the straight current carrying conductor, right? So here the distance being different, magnetic field would be different at different points. What's the angle between B1 and DL1? B1, it's along this direction, DL1 will also be along that direction. It will be given tangential, isn't it? So angle between these two is 0 degree. So it is DL1 cos 0 degree. This is the dot product. Again, B2 vector dot DL2 vector. It is magnitude of B2, magnitude of DL2. What is the angle between these two? Strength of the magnetic field as well as elementary portion. Again, both are in the same direction. At any point, it's given by drawing a tangent. So angle is again 0 degree and so on. So it will be strength of Bn, magnitude of DLn, and again cos 0 degree. Clear, students? So cos 0, as we are aware, is equal to unity 1. So we will be left with B1 DL1 plus B2 DL2 plus B3 DL3. So dot product gets eliminated. So plus Bn DLn. Okay, student. B1 is the magnetic field at this point due to this infinite long straight current carrying conductor. And this point is at a distance of R1 from this straight conductor. So what is the strength of the magnetic field? As per Circuital law, it is mu naught I divided by 2 pi R1. Yes, students? B2. It is the strength of the magnetic field at this point due to again the same straight current carrying conductor. And here the distance is R2. Effective distance is R2. So the strength of the magnetic field B2 would be mu naught I divided by 2 pi R2 and over here DL2. Understood, students? Similarly, B3, it will be mu naught I divided by 2 pi R3 and this is DL3. So this distance R1, R2, R3 would be different at different points because of the asymmetrical nature of the loop. And lastly, for the nth one, it will be mu naught I divided by 2 pi Rn and this is DLn. Right? So now what to do is, okay, let me write another step over here. We can take common over here. Mu naught I divided by 2 pi. It can be taken as common. So we will be left with DL1 over R1 plus DL2 over R2 plus DLn over Rn. Clear, students? Now concentrate on this particular diagram. Concentrate on this particular diagram. Now this is a small elementary portion of length DL1. Now this can be considered to be an arc of length DL1 and radius R1. And we are aware of the relationship between angle, length of the arc and radius. So angle, it would be given by length of the arc divided by radius. Isn't it? Similarly, students, this one, DL2, it can be considered to be the length of an arc of radius R2, subtending an angle d theta 2 at the center. So accordingly, angle is length of the arc divided by radius. So here what we get is d theta 2, it will be equal to length of the arc divided by radius. Clear? And so on. Similarly, angle subtended by the nth elementary portion DLn at the center may be considered to be d theta and its radius can be considered to be Rn. So d theta angle would be equal to length of the arc divided by radius. So we can substitute this value over here. What we get? Mu naught I divided by 2 pi dl1 by r1, it can be considered to be d theta 1 plus d theta 2 plus d theta n. Right, students? Now look, d theta 1 plus d theta 2 plus d theta 3 plus d theta 4, if we add these elementary angles, it will give us the net angle of 2 pi radians, isn't it? The total angle subtended at the center by a circle or by a closed loop is always 2 pi radian. So do the d theta 1 plus d theta 2 plus d theta 3 and so on will amount to 2 pi radian. So it will be equal to mu naught I divided by 2 pi multiplied by 2 pi. So that will give us mu naught I, which is equal to RHS. So this is how you can prove this particular law for asymmetrical loop, right? Thank you.